Start from current slide. All right, finally we're here. We're ready to get started. Sorry we're so late. Just a little bit of recap of where we were, what we're doing. We finished topic 16 last time, which means today we'll have the lab on topic 16. And I've still got a little bit of things to set up for that, but there have been people in and out of the lab, so I didn't want to set up and then have somebody come in and mess it up. So we'll have to set up when it's time. So we will stop this at 7 and start the lab. So it's almost 6 now, so we've only got a little over an hour to go. So we'll get going on topic 17, and that's current and resistance. And we'll get as far as we can today, stop at 7 o'clock, do the lab from the last, and then I'll give you the test from 16 as well. By the way, if any of you have to leave early, please don't leave without the test, because I have it ready. That's the other thing I had to do. I had to go down and make copies, because I thought the other lab would get through early and I could have time to make my copies. They didn't get through until late, and I just did. By the way, several people left things in the lab, and you two were there. This is Tierra Bradford's. This is somebody's notebook. I don't know whose. This is someone's red pen and someone's blue red pencil and blue pen. So they're up here if anyone knows next time, if anyone's missing. The notebook has their next lab test in it, so they left their test and their notebook. Okay, but I didn't want to leave them in the lab because I was afraid they would get walked off by a biology person. All right, any questions on anything we've done up till now or how we're going to proceed from here? All right, current and resistance. The applications we've talked about so far have all been based on static electricity, okay? Actually, including capacitance, this is a form of static electricity as well, but later we'll see that can be used in circuits, okay? But a steady source of electric charge is called a current. That allows students, scientists to learn how to control the flow of electric charges in circuits. So that's what we're talking about now. Current, which is the flow of charge, and resistance. Okay? The current is the rate at which charges flow through a surface. Now you might say, what surface are they talking about? It's an imaginary surface. Let's say we have a wire here that's carrying the current. The charges are moving down that wire. Just imagine there was a surface across there. How many charges are crossing that imaginary surface in a given time per second, say. Okay? So look at the charges flowing through perpendicularly through a surface of area A, and the average current would be the change of charge over the change of time. Sort of dq dt. The SI unit for current is the ampere. So therefore, an ampere would be 1 coulomb per second. Ampere is 1 coulomb per second. Now remember, a coulomb is a fairly macroscopic unit of charge. Okay? Lots of little electrons. Okay? Second is a pretty good length of time. So ampere is a macroscopic measure of current. Okay? Now, depending on what you're dealing with, if you're dealing with something that's drawing a lot, that's producing a lot of heat, you're using several amps, okay, of current. If you're doing something like running a computer or a calculator or something like that, you're probably using milliamps. So it's a wide range of currents that we deal with, okay. Now, instantaneous current is the limit of that average current as the time interval goes to 0. That's nothing new for you, is it? Y'all were all in, either were in 201 or you're in it now, and when you did instantaneous velocity, it was the limit as change of position over change of time as the change of time went to 0. Instantaneous acceleration, change of velocity over change of time as the change of time went to 0. So instantaneous current would be the limit as that delta t goes to 0 of that average velocity, which would be the limit, average current. That would be the limit as delta t goes to 0 of delta t over delta t, as that delta t gets smaller and smaller and smaller. If there is a steady current, the average and instantaneous currents will be the same. And we'll usually assume that they're usually fairly stable static currents. Now, when we start doing some of the experiments in the lab, you'll see that some of our power supplies are probably not quite up to par, and they do a lot of fluctuations. But we'll try to assume that they are the same. The SI unit, again, for both instantaneous and average current is the ampere. Why is it capital A? Why is the unit a capital A for ampere? Named after somebody. Louis, I think it was Ampere, a French physicist. And by the way, if you haven't noticed, Coulomb French, Ampere French. The French were sort of the leaders at this time, because France at this time was sort of the peak of their society. This was around the time of Louis the 12th, 13th, 14th, Louis the 16th. Those were very prosperous times in France, and their science benefited from it. So about the same time, remember that Benjamin Franklin was an ambassador to France. He did a lot of the early work in electricity here. I'm sure he colluded with some of those guys when he was over in France. I don't know that for sure, but I'm fairly certain he must have. Okay, continuing with current, electric current. This is that imaginary surface. The direction of the current is the direction a positive charge would flow. Herein we run into some difficulties, don't we? Because in reality we know usually the negative charges are the ones that are moving. Positive charges are protons. They don't move, okay? Cations, they don't move very much, okay? It's the electrons that do, but our convention is the direction of current is the direction that positive charges would be moving if they were moving. That is known as your conventional current direction, the direction positive charges would be. In common conductors, such as copper, most of the things, the current is due to motion of negatively charged electrons. Now that's an overstatement itself too. So in reality, the charges are moving this way, but because they're negative charges, the current is still considered to be to the right, even though the electrons are moving to the left. Okay. Now, one other feature here, the C part, is common to refer to a charge as a mobile charge carrier rather than the charge. The moving charge is a mobile charge carrier. The charge carrier could be positive or negative. In fact, in today's lab, I think most of the last chapter I was assuming the lab would be strictly on capacitance. The more I thought about it and reviewed what I had done before, I found out that the previous book that we used before we used this one, not the previous edition, but the previous book, it split capacitance and voltage into two different chapters. Well, this book combined them into one. The voltage experiment, I think, is a lot cleaner, neater, easier to determine than the capacitance lab. So today we're not doing capacitance, we're doing voltage. And it'll be a pretty quick lab. I think you'll find it goes pretty well. But one of the things we'll be doing in today's lab, I will be putting salt into water. Okay? Why would I do that? To form the electrolyte to actually carry the charge. then I'll place into that, or y'all will, parallel plates. There'll be different materials, okay? Copper and aluminum, say. Well, when you put two different plates into an area that has charges, meaning ions, then actually what happens is both the positive and the negative charge carriers move, and that's typical of a battery. In a wire, it's mostly electrons moving, okay? You don't have any other charge carrier to speak of. But in a battery, that's typically what you have. So, for instance, if your your negative charges, like your chloride ions, are moving in this direction, typically your sodium ions will be moving in the opposite direction. Okay? They're showing this as a conductor, and that's certainly okay. But in a battery, you actually do have positive and negative charges moving in the opposite direction, but the current would be the direction positive charges were moving, if that's all that were moving. Okay? Does that kind of make sense? Okay. That's the bottom of page 567. Okay. Now there is an example 17.1. If you want to do that, certainly willing to do so. But there's a quick quiz on the bottom of page 568. And let's listen up for this one. Yeah, some of you have your books. I don't know if all of you do, but consider positive and negative charges moving horizontally with the same speed through 4 regions. Okay? Yuck, I'm going to have to draw this one, am I not? Okay, let's see if there's any. I'm going to draw it on this one, okay? Consider positive and negative charges all moving horizontally with the same speed in the 4 regions in figure 17.2. Now, some of you have your book, but some don't, so I'm going to try to do this. Okay? Here's the A picture. Oh, goodness, let me get my pen set up. Okay, here's the A picture. There's your little segment of wire, and we have a negative charge here moving this way. We have a positive charge here moving that way, a positive charge here moving that way, a negative charge here moving that way, and a positive charge here moving this way. All moving at the same speed. My arrows aren't the same, but you got it. Okay? It's an ugly picture. Hard to see. Okay? Now, the B picture. This is A. I'll try to draw B a little bit better. Okay? Here you have a positive going this way, a positive going this way, and a positive going this way. Okay, all 3 positives going to the left. Okay, that's B. Here's C. Oops. Okay. Here's C. You have a negative moving this way, a positive moving that way, another positive moving that way, and a negative moving this way. Okay? And the last one, that's C. I'm going to do D over here. And what we have is a negative moving that way and a negative moving that way. Okay? That's D. All right. Now, since you have charges moving, okay, at a uniform speed, all the speeds are the same for all charges and all pictures, okay? What the question is here, consider the positive and negative charges moving horizontally in the same speed in all 4 regions in this figure. Rank the magnitudes of the current in these 4 regions from lowest to highest. Now notice they said magnitude, not sign, magnitude of the currents in from lowest to highest. Okay? IA, this would be the current I sub A, I sub B, I sub C, and I sub D. Okay, we're not messing with signs here, just magnitude of the current. Okay, same charge size, same speed. Now this had 2 negatives in this direction, 3 positives in that direction. What would be the magnitude of that charge? Three positives in that direction, 2 negatives in this direction. What's be the magnitude of the charge? Say again? Okay. 3 positives moving that way, 2 negatives moving that way. What would be the magnitude of the charge, of the current? I sub A. Okay. We're not worried about the sign. We just want magnitude. You got 3 positives that way, 2 negatives this way. What would be the magnitude of that charge? Make a guess. 0. No? Huh? Yeah, it's a number. 1. Okay. You subtract them. Now, if the negative had been moving in the same direction as the positive, you would have subtracted. But you got the positives moving this way, the negatives moving that way. Huh?
You subtract them. No, he said it moving in the same direction. So do you add?
Yeah, so that would be 5. Okay, that would be 5. A sub I would be 5. Now we don't know if it's coulombs per second, which would be amps. It would just be magnitude of 5. What about this one? 3 positives, both moving, all moving in this direction.
0. No way. I'm confused.
3 positives, all in this direction. 3, of course. So that would be magnitude 3. Same charge, moving in the same direction. 3 of them. What's that?
But it's not going in the opposite direction.
So, okay. This, the 3 positives going this way would be 3. The negatives moving this way would also be, because if that was positive, these would be moving this direction. That would be 2 positive. So, see right up here? This would be 5 positive charges in that direction. It would be 5 in that way. 5 negatives in this direction is still 5 in this direction. So if you had those going through the same wire, then that would be 10, because of plus 5 and plus 5. Okay. Now if these negatives were moving in the same direction, then they'd be subtracted. Because you have the positive going this way and negative, they cancel each other out. These, that would be 5. This would be 3. How about here? Now this one we had 2 positives in this direction, 2 negatives in that direction. 4. Good. That would be I sub C would be 4. Okay? And I sub D would be 2 negatives in that direction. 2. Okay? So how would you rank these? And it says from, rank the magnitudes of the currents from lowest to highest. Okay? It would be I sub D, comma, I sub B, comma, I sub C, comma, I sub A. Okay? Now, DBCA. DBCA. That looks like number or letter D, doesn't it? Let's see what they say in the back. They better say D. 17, topic 17, A is D, 1 is D. Got it. All right. More than what I had intended to do. Okay, now, that's called, if you're talking about coulombs, that's a macroscopic quantity. Amps is a macroscopic quantity. But if you're talking about actual electrons moving, or charges moving in a battery, ions moving, you're talking about something far, far, far smaller. Okay? Now, this section in the text, 17.2, I don't see where they're covering this here. So I'm going to have to look and see if I can find, here we go. I don't know why they introduced power here. Since they did, I'll read the slide, but it's going to be somewhere else in our book. So let's look at power now. This is out of place. Makes no sense here, but let's do it. In a conductor carrying a current, the electric potential of the charges is continually decreasing, right? If the conductor is carrying a current, the electric potential of those charges is decreasing because they're moving in the direction of lower energy. So the potential is decreasing, right? The positive charges move from regions of high potential to regions of low potential, and that change of potential, that's what this is, delta U, the change of potential, right? Change of potential energy. Here we get. Sam's here. All right. Just missing 2 of our regulars and then 3 others we haven't seen ever, but they're on the roll still. As far as I can tell, they haven't paid, so I'm guessing they're not going to be on the roll much longer. As soon as I can get them off the roll, I'll be returning some papers to you. So, what's that? They're not coming? You're sure? Okay. Yeah, I don't think they are either, but the administration has kept the names on the roll. If y'all are that certain, which I think you're probably right. Huh?
Are we 4 weeks in or 3 weeks in? This is 3rd week?
Something like that, yeah. Was there a question there? Okay. Let me see if there's anything I can return to you yet. So what have we got? 7 regular attendees, 7 paid. Lab 1, 2, 3, 4, 5, 6, missing 1. Okay. So I know I can't return lab 1 to you. Oh, you have it ready? Okay, well then I can return it to you. I don't mean to rush you, but you got it?
Yeah.
Okay. What's that? Okay, you mean pause it? Is that what you said? Yeah, it doesn't hurt to. All right. Now, this is the change of potential energy, delta U, of the charges is, remember, Q times delta V. Okay? How I remember this is voltage is energy per charge, so their energy is charge times voltage. Okay? Now, that means that the change here is negative because the charges are moving in the direction to decrease the potential. Often only the magnitude is desired. Okay? Well, in reality, direction really doesn't matter here anyway. These are not vector quantities, so really the only thing that we do care about is magnitude. The power delivered to the circuit element is the energy divided by the elapsed time. So let's go back. If this is energy, divide that by time, and you get the power. Why they put this slide in here is way out of place, but I just want to point out to you, if you divide this by delta T, and also divide this by delta T, this will be energy per time is power, and over here, charge per time is what? change of charge per change of time. What is that called? Change of charge per change of time. Say again? Not voltage. Current, exactly. Charge per time, coulombs per second. That's in amps. So what we have over here then is power is equal to amps times volts. Hang on to that idea. We'll be covering that in a later chapter. Okay? But that is what we got. Power is delivered to a circuit element. Energy divided by time, which is current times voltage. Okay. Now we're ready to where they are here. I don't know why they threw that slide in where they did, but here's what we're doing now. Current and drift speed. Okay, this is 17.2 in the new edition and in the old edition as well. Let's see what the other was. That other was just the end of 17.1 and I see, yeah, there was that last paragraph there, they did cover power there. A little bit. I'm not even sure they mentioned the word. Okay. Not enough for a slide. So current and drift speed. Charged particles move through a conductor with a cross-sectional area A. That's what defines current, right? N is the number of charge carriers per unit volume, whatever that is. N times, okay. A times delta X is the total number of charge carriers that are moved. Because if you have the area times the, area times the change of distance here, that gives you a volume. If N is the number of charge carriers per unit volume, then N times A times delta X is the total number of charge carriers you have moving. Okay? Now, they said nothing about time here. If you measured the time for that, then you could back up and get what the drift velocity was. Okay? The V sub D, that's the drift velocity of these, that times the time, this is meters per second times second, that would give you your meters. Okay? The change of distance would be the drift velocity times the time interval. Okay? So, the total charge is the number of carriers times the charge per carrier, Q. Okay? Now, this is the first time this has come up that I recall anyway, and it is something to sort of make a note of. The total charge is usually capital Q. The charge per carrier is little q. So if these carriers were electrons, that would be the electron charge. If they were ions that may have a +2 or a -3 charge, that would be the Q for those ions. So this total charge is this number of charges times the charge per carrier. Number of carriers times the charge per carrier. The drift speed, that's the V sub D, okay, is the speed at which the carriers move. Okay? So if you take the drift speed is delta X over delta T, that's usually what our average speed is, right? The drift velocity, that would be delta X over delta T. So if you were to divide this part by delta T, then this would give you a V sub D in here, and that would be charge per time, that would be a current. So what we have there is delta Q equal to N A, and then if delta X is V times VD delta T, then this would be your V sub D delta T times Q. And then the current would be divide this by delta T, dividing this by delta T, Divide this by delta T, those go out, you have N, Q, A times the drift velocity. So, okay, big deal, okay? To me, all you need to remember is this. If you ever need microscopic, that would give that to you, okay? Now, if the conductor is isolated, the electrons then just undergo random motion. If it's isolated, there's nowhere for them to go. The charges can't move very far. They just move by random motion. When the electric field is set up in the conductor, it creates an electric force on the electrons or on the charge carriers, and then they move, and then you've got a current. So as soon as you set up that potential difference across there, you're going to have a current. All right. Now, what is this actually like? Now, this is figure 17.4, the bottom of your page 569. Where are these electrons? What are they actually doing? Okay. Now remember, the electrons on average move in the opposite direction of the electric field, because the electric field would be the direction a positive charge would move if it was moving. The drift velocity of these electrons are in that direction because they're moving that way. Do they really just drift along in this direction? No. They can run into all sorts of things. They could run into an atom here and get deflected upward. They could run into another electron here and get deflected backwards. They could run into another electron here and get deflected backwards again in that direction. Then they could bump into, say a positive ion and be drawn. They can just do all sorts of zigzaggy, and this is called tortuous motion. Okay, but the general drift is in that direction. Although the electrons move with an average velocity v sub d, the collisions with atoms cause sharp, momentary changes in direction. And that every one of those is a collision with either an atom or possibly another electron. Usually an atom. It could be an ion too, but usually it's with an atom. They're going to hit them. Guaranteed they're going to hit them. Okay? So, the zigzag backline represents the motion of the charge carrier and the conductor. The net drift speed is incredibly small. The sharp changes are due to collisions with something else, usually atoms, possibly other electrons, possibly other ions. The net motion of the electrons is opposite to the direction of the electric field, like we already said. Although the electrons move with average velocity that way very, very slowly, collisions with the atoms cause sharp, momentary changes of direction. So these actual motions here can be quite fast, but the average drift velocity is incredibly slow. Okay. How do you account for it then? I flip the switch and the lights come on almost automatically if the drift velocity is that slow. If it was just depending on the electrons leaving that switch and going to the light bulb, it would take literally hours for the light to come on. Well, that's not what's happening. We'll get to that later. Okay, but just a heads up. So, the electrons in a circuit, or charge carriers in a circuit, assume that you close the switch to turn on a light. The electrons do not travel from the switch to the bulb. Probably ever. Okay? The electrons already in the bulb move in response to that electric field that's set up by the completed circuit. So in other words, when you flip the switch, what's happening is the field is set up just about immediately. Field speed is incredibly fast. Electron speed, unbelievably slow. Okay? So it's not the electron motion, it's the field being set up. Well, there's charges all in the wires and in the bulbs and everywhere else in the system, As soon as the field set up, and almost instantaneously, they all start moving at the same time. Those right there, those right there, those right there, and certainly those in here. So that's why the light comes on immediately, or close to immediately. Okay? The electron's already in the bulb, moving in response to the electric field set up on the completed circuit. A battery in a circuit supplies the energy, not charges, to the circuit. Remember what the battery is? It's energy per unit charge. It's not charges. It's not supplying electrons or protons or ions. It's supplying energy to those charges. That's what a battery does. And we talked about batteries last time. That's what the lab will be on this time. So the electrons in a circuit, the drift speed is much smaller than the average speed between collisions, big time, because some of those average speeds are in the opposite direction or near opposite direction. When the circuit is completed, the electric field travels with a speed really close to the speed of light. The field travels at that speed. It's set up at that speed. The electrons are incredibly slow. Although the drift speed is on the order of 10 to the minus 4 meters per second. Okay? Someone tell me what 10 to the minus 3 meters is. 10 to the minus 3 meters. 10 to the minus 3 meters. To the minus 3 meters. What's that? 0.001 meters. And what would that be? 1 millimeter.
Oh.
1 millimeter. That's about the thickness of a dime. Okay? That would be 1 millimeter. 10 to the minus 4 meters would be a tenth of a millimeter. So take that dime, okay, and slice it into 10 equal slices. That's really small, isn't it? That's how far, that's the drift speed of an electron. It would show just 1/10 of the thickness of this dime. In other words, it would take 10 seconds for the electron to travel from one face of this dime, the head of the dime, to the tail of the dime. 10 seconds to get there, okay? The effect on the electric field is felt on the order of 10 to the 8 meters per second. That would be 100 million meters per second, okay? Incredibly fast. That would be, I think, about 4.5 times around the globe in a single second. This would be 1/10 of the thickness of a dime in a single second. You talk about a huge difference in speeds, right? So let's move on to circuits. This is 17.3. Before we go there, let's do quick quiz 17.2. Suppose a current carrying wire has a cross-sectional area that gradually becomes smaller along the wire so that the wire has the shape of a very long truncated cone. How does the drift speed vary along the wire? What would be your guess? How would the drift speed change, say, when the wire was this big, and then as you moved along the wire, it got smaller and smaller and smaller? What would you think would be happening with the drift speed? Could be what? Okay, you're absolutely right. The drift speed would have to increase because the electrons going through a given area, if that's all the same speed, okay, then as the area gets smaller, more electrons would have to go through there faster, okay? Okay, that's at least what it would have seen, okay? How does the drift speed vary along the wire? It slows down as the cross-section becomes smaller. It speeds up as the cross-section becomes smaller. It doesn't change or more information is needed. I think you went with B, didn't you? Okay. See what they say in the back? B. Very good. All right. A little tip is here. Electrons are everywhere in the circuit. Everywhere in the circuit. So as soon as that field hits, they move. All of them move simultaneously. None of you have been in the military, have you? Okay. In the military, they like to do drill, close order drill. And what they like to do is when they say forward march, the whole unit moves at the same time. It's not that like a string of cars, this one moves first and then these move and then those move. The whole thing moves at once. And if you had a huge, long line of marchers, when you said forward march, they all move at the same time. That's what's happening in electrons are everywhere in the circuit. As soon as that field hits, they all move at the same time. Not very fast, but they all move at the same time. All right, so 17.3. A circuit, sort of like the word implies, is a closed path of some sort around which the current circulates. Okay? A circuit diagram can be used to represent a circuit. Okay? Quantities of interest are generally the current and the potential difference. Okay? We'll hit more quantities of interest later, but for right now, current and potential difference. Okay? There are two types of meters that we typically use in a circuit. There will be others later. The first is an ammeter. What you reckon it's measuring? Meter is to measure. What does that almost look like? Put a P on it, and that would be amps. That's measuring current. Okay? Now, in order to measure current that's flowing through, say, a bulb here, what you have to do is make sure that your ammeter is in the circuit. It can't be outside the circuit. So from the battery, again, remember conventional current is in the direction that the positive charge would move, even though most of these are electrons moving in the opposite direction. So the positive charge would move this way through the bulb, and then all the current that goes through the bulb needs to go through the ammeter as well. Okay. That's used to measure current, so you need to measure it all. It's in line with the bulb, and the charge passing through the bulb must also pass through the meter. Now, they haven't shown the voltmeter wording yet, but they got that here. And here's the battery here. It's sending the positive charge, the current this way, through the light bulb, and then that same current goes through the ammeter, and that's what you're measuring for 835 ammeters, or 835 milliamps, going through here, going back to the battery. Now, the next slide is going to talk about the voltmeter. The voltmeter only measures a potential difference across this. Very little current goes through the voltmeter. Certainly a little bit has to, but not very much. Most of the current goes through there. That's why this is negligible, the current going through. But this measures the voltage difference across there. And this measures the current. And later we'll see that together they give you, we'll get there later. Okay. The voltmeter is used to measure the voltage or potential difference across the bulb, or across the battery, or across the ammeter. It's connected to the two contacts of the bulb. Now this shows it connected to the wire, but you have to actually pierce the wire. Usually you connect one here and one there. Okay? That measures voltage, potential difference across the load, the bulb. Okay. Now that we have those two pieces in place, there is a quick quiz before we get to resistance. At the top of your page, how many of you have books or something you can see the figures? I see 2 right here. Any others? Just 2. So I'm going to have to draw this again, I guess. Okay. Let's see if I can find a decent place to draw. I think I'll draw them here. Okay. Now, well, wait. I'm going to draw them like this. I'm going to draw not the actual circuit, but the circuit diagram, just like that one is. Okay? Oh, no. That would be so hard to draw here. I'll tell you what. I will use this picture they have here. They have a car battery, it looks like in the book. I'm going to use these 2 little batteries there. Just picture that as a car battery. Forget about the ohm meter and the amp meter. We're not going to use those in this thing. Here's what the first will be. Not the yellow line there, but what we've got is the positive from the battery going to this side of the light bulb, okay? And from this side of the light bulb, it comes back to the positive side of the battery, okay? Now, there's number A. This is A. Bizarre. Okay? Here's B. You have your battery, the positive side of the battery. It goes to one side of the bulb. Again, we don't have a voltmeter or ammeter. Goes to one side of the bulb. Okay, right there. Then, from here, from the other side of the bulb, you have a loop that just does like this, and then it goes back from this side of the bulb to the other side of the battery. So there is your second circuit. That's your B. These are totally strange. Totally strange. Okay? I don't know why it changed, but I'm going to let it change. Here's C. It goes from the positive side of the battery to the bulb. Again, the ohm, voltmeter and ammeter are not in the picture. Goes to the load. Then from here, goes directly back to the negative end of the battery. That's your C. Okay? Your D. It goes from the positive pole of the battery, again, no ammeter, no voltmeter. Oh, wait, no, sorry about this. Sorry. Which does it have here? Oh, that's ammeter. Okay. So let's get that corrected. It has an ammeter, but it doesn't have a voltmeter. Okay. It says it goes from the positive pole of the battery to the one side of the light bulb, from the other side of the light bulb to the positive side of the ammeter, and from the negative side of the ammeter goes to the negative pole of the battery. Okay. Now, this is D. Now, those are not particularly great drawings. If you had your book, you'd see the drawings maybe a little better, but they're bizarre drawings. So there's A, B, C, and D. Okay? Now, what the question is, look at the 4 circuits shown in this figure. Select those that will light the bulb. Will A light the bulb? Say again? No. You're going from the positive side of A through the bulb back to the positive side of A. You have no potential difference here to get the electrons moving at all. No energy is being supplied to the charge, so the charges don't move. A's out of the question. How about B? No. Okay, what you have here is from the positive side of the battery down to the bulb, then from that same side of the bulb up to the negative side of the battery. No, I'm sorry. And a loop over here on the negative valve, on the other side of the bulb, and then back to the negative side. There's no way. All the current's going to go through here and not going to even touch the bulb at all, and this loop goes out of nothing. So that bulb won't light. So B will not light either. How about C? Yes, C certainly will light. You go from the positive side of the battery, the current flows to the bulb, from the negative side of the bulb back here to the negative side of the battery. Yes, bingo, it worked. Oh, you can't say bingo now. Okay, how about D? Yes, all you've done is put an ammeter in the circuit, which is fine. It just measures how many amps are going through there, but it leaves the positive side of A, goes through the bulb, through the ammeter, and then back to the negative side of the battery. For sure, no problem there. So it should be C and D. Let's see what 3 is. 17, 3, C and D, good for them, they got it right. Okay. Now we move to Georg Simon Ohm, or something like that. Simon, I don't know. German, that's Georg, strange pronunciation. Simon, I guess it is, Ohm. He lived in the late 1700s, early 1800s. So to put him in history, he was born about the time of, this was the time in between our Articles of Confederations and the Constitution. That's right around this time frame. Right at the beginning of the Constitution, or just a little before that. 1854, that went right before the war between the states started. Okay? So, born in that time frame, or lived in that time frame. He formulated the concept of resistance. Okay? Really a decent thing. He discovered the proportionality between currents and voltages in most circuits. Not all circuits, but in most circuits, he found there was a proportionality there. Guess what the concept of proportionality was? The resistance. Okay? So basically, that came out of this. Okay, I would have put those in different order. Okay, so what have we got here? Resistance. In a conductor, these are conductors, by the way, the voltage applied across the ends of the conductor is proportional to the current going through the conductor. Okay, you got that? Voltage applied across the ends of a conductor is proportional to the current flowing through the conductor. The constant of proportionality is called the resistance of that conductor. So in a conductor, the voltage applied is proportional to, so you could say, if you use that symbol, you would say the voltage applied, delta V, is proportional to the current flowing through that resistor. Okay? Okay. Thing is so slow. To change that, you would put to an equality, it's delta V is equal to some K, constant proportionality, times the current. Okay? Then if you were to divide both sides by the current, then that constant proportionality is what we call the resistance. Okay? Constant proportionality, that is the ratio of the current, the voltage difference to the current. Okay, that leads to, that's almost exactly Ohm's law. Okay, and by the way, the units for resistance are named after Georg Ohm, called an ohm. Okay? Now, according to the usual convention, remember, Volts were named after the Italian physicist named Volta, so it's a capital V. The current is named after the French physicist Ampere, and those are called amps. So what would we typically use as a symbol for an ohm? If capital V is voltage, capital A is amperage, named after Louis Ampere, what would you call ohm, typically? Capital V for voltage, capital A for amperage, capital O. So why do they use an omega? Well, let's just say, give me a number, any number.
27.
27. 27 ohms. What's wrong with that?
That's 270.
It looks like 270. So, yeah, you can't use a capital O. So they went to the Greek alphabet. And in the Greek alphabet, the letter that corresponds to our O is Omicron. But guess how Omicron looks? Just like an O. Okay? So you couldn't use that either. But guess what? In the Greek alphabet, there is another letter that doesn't correspond to any letter in the English alphabet, and it's the very last letter in the Greek alphabet. Anyone know what it is? Omega. Have you ever heard the alpha and omega?
Yeah.
What does that mean?
First and the last.
First and the last, exactly. Yeah, the first and the last. So that's what it means. So the omega also starts with our letter O, but the symbol, and that, by the way, is a capital omega. A little omega looks like this. We'll use that for frequency later on, but that's not anything we're going to use now. Because it was named after a person, we use the capital omega. Now, this is the unit for resistance. Resistance in a circuit arises due to those collisions between the electrons carrying the current and the fixed atoms inside this current, the conductor. They're going to happen. They always happen. And the resistance arises because of those collisions. So you can't have a circuit with, well, a normal circuit with no resistance. There's always going to be a resistance. There's always some ratio between the voltage applied and the current that's moving, and that's your resistance. And 1 ohm is 1 volt per amp, or R is equal to delta V over I. Now remember, V, the volts, that's the symbol for the unit. It's also a symbol for parameter. R is the parameter. Omega is the ohm, is the unit. I is the parameter for current. A is the unit for current, ampere. Okay. Now, I think I'll end with a dumb story. But it's true. It's not dumb, but it's true. Physicists are a little bizarre, just a little bit. There is another thing that physicists talk about and measure sometimes in currents, and it's not the tendency to retard the motion of the current, like resistance is, that resists the current flow, but it's the inverse of that, the conductance of that material. So conductance, by the way, conductance is equal to 1 over resistance. It's a reciprocal quantity to resistance. Okay? So, guess what unit they use to measure conductance? It's 1 over resistance. And frankly, I don't know, and I don't know if anyone actually is identified as coming up with the concept of conductance. So they needed a unit. They couldn't name it after anybody because they didn't really have anyone to name it after. So what could they name the unit for conductance? And conductance, remember, is 1 over resistance, the reciprocal of resistance. Say again? What could we name it? Say again? Who knows? Okay, what would we name it? Okay, you probably,
She's telling the story.
what did she tell you?
Yeah, what did I say? She said,
No, that's charge,
yeah, I
okay?
know, that's why I said to you, you're wrong.
Okay, all right.
Is it that backwards?
Hey, look at that. The unit for conductance is a mho. A mho. And where did mho come from? Is that Frederick Mho who came up with this?
Backwards.
You spell ohms backward. I told you physicists were a little bizarre. No, they're very bizarre, okay? Now, what symbol could you use for mho? I don't think we can use M. We already have that for meters. MH wouldn't make a lot of sense. I hate to have to spell that out. So what symbol could we use for a mho? Remember, a mho is an inverse ohm. What symbol they use for a mho? And upside down, the inverse of an omega. That's not a symbol. There's not in anybody's alphabet. It's just an omega they turned upside down. Because what is it? It's 1 over an ohm. So they just flipped it over. Really bizarre, aren't they? Okay. Okay, it is lab time. Let's see what the next slide is. The next slide is Ohm's law. That's where we'll begin next time. Okay? All right. Now, I'm going to pause the... All right.
Does it have to be positive?
Wait. Okay, we'll get to that in a second. Okay? We had 1410 millivolts, right?
Yeah.
Well, a millivolt, if we're trying to get to volts, then what we would do is put volts in the numerator, millivolts in the denominator, and how many millivolts make a volt, or how many volts make a millivolt? 1,000 millivolts, that's what milli means, makes 1 volt. So that means we can move the decimal 3 places here, 3 places here. The millivolts cancel out, and that gives us 1.41 volts. Okay.
So we write that in the morning.
Say again?
We write that in the
Okay, yes. Now what it says here, let's read the thing. Place 2 different electrodes into a container of salt water. We've done. Connect to a voltmeter. We did. If no voltage is measured, try reversing polarity. We did measure one. Circle the metal that is connected to the positive electrode. It gave you the positive there, and that was the carbon. So circle the C and record the potential difference measured. 1.41 volts. Very good. Okay?
So it has.
Now,
Can we do one more
we're going to do that many more.
together?
Okay. Well, y'all are all together.
With you.
Oh, with me. Oh, okay. Okay, you want to do aluminum copper now?
We just did that one.
No, we did aluminum carbon.
Oh, yes.
Aluminum copper. So I'll take out the carbon. No, people have broken all my other ones. That's such a shame. Okay. That's carbon. Remember that one's carbon. And who had the copper? You did, didn't you?
Oh.
Okay. All right. Even though they're not touching, which is good. So I'll let one of you do the honors there.
So, you know when you were saying, like, which one is positive?
Yeah.
How do you know? Is this positive, negative?
Yeah. You see, yeah, this is the common, which is the negative side, and that's on the plus side. And then you read the number up here, and if it's plus or minus, then it's swap. If it's minus, it's swap. are you getting? All over the place. Okay, it seems to be something. 1100, that's good. 1100 millivolts. Positive, so the positive is on the copper. So circle the CU for copper. Yeah. 1100 millivolts would be 1.1 volts. Got it?
Yeah.
Okay.
Wait, so how do you know it's positive again? It
Okay.
is
Yeah, you see this thing here?
Yeah.
Okay. You see, when you did this way, I don't see a sign. When you do it this way, you see the minus in front?
Oh, so when they black?
Yeah, that right there is the minus.
Oh.
See, there's minus.
No, I'm saying these.
Okay.
The red one is positive.
Red one's the positive, because that's the, this is the main and this is the return. It's just sort of standard. In your car batteries,
Okay.
you always do the. All right. Now y'all can start swapping out. Okay. Okay, so we leave aluminum in, and okay, you have to unscrew it probably. Okay. And if y'all have any problems, I'll be right here.